Hello all, I welcome you all to the second lecture of this course, EE698EM. In the last lecture, we had the introduction to electrons and photons. We had some basic idea of experiments which were conducted from 1600s to 1900s. And then we saw some landmark experiments, right? And today we will continue that trend a little bit further, and then we will see some important properties of solids, and then we will first construct a classical theory of electron transport, how the well-known Ohm's law was formulated or well understood in early 1900s and such. Okay, so today we will probably study more about metals, but before metals it is just solids or condensed matter, right? So solids were among the most studied. There are different kinds of solids, and people knew about metals particularly because metals had some important properties. The first one being they were all shiny and lustrous, right? I mean that they were bright to look at, and that's why they were probably used in many circumstances. Two, they were malleable. And ductile, in the sense they can be beaten to sheets, they can be drawn as wires. So this is one property which was very useful in metals. The other kind of solids, like say insulators and ceramics, were often brittle. Right. So this was also obvious in a relation called they sustain significant elastic deformation. So what we mean by this is it had some linear relation between the stress and the strain, which we call as Hooke's law. So if eta is the strain, so it was related by something like say Y and E. Y is called the Young's modulus, E is the stress, and eta is the strain, right? So this is called the Hooke's law. And other materials like say commonly used wood, ceramics, they all broke when you have some strain, and it was not did not bend and such, right? So they were not used in constructions and such. The other property which was particularly useful were they were used as they had good thermal conductivity, right? They were used in making cooking pots and utensils and such. They had good electrical conductivity. We will see about this because these two are the important aspects of discussion for the lecture today. So metals had both good thermal conductivity and good electrical conductivity, and materials which were not good thermal conductors were also not good electrical conductors. So this was the point of contention. So there was, so let's say the thermal conductivity was represented by, let's say, kappa, and the electrical conductivity was represented by, say, sigma. It was found that kappa by sigma always had a constant relationship for most materials. L was called as the Lorentz constant, and T is the temperature, right? This particular relationship was called as Wiedemann-Franz law, right? So he found that the ratio of the thermal conductivity to electrical conductivity for most metals were constant, and this is also true because in other non-metals, but then the relation is not just the same, right? They were not very good electrical conductors, so basically you will not be able to measure these values for non-metals. For metals where these measurements were available, the ratio was turned out to be almost a constant and dependent only on temperature, and this is something which was, I mean, at that time was not well understood. Why is this true, right? Because the reason for electrical and thermal conductivity was not yet well known. Thermals conduction was studied for a long time by Lord Kelvin and others, it was always thought to be some sort of a fluid. The same fluid was thought to be the reason for electrical conduction. We will see soon enough. But that there are some particles which are useful for electrical conduction came about by the thought of electrons. But later Maxwell came and turned everything and said that you should consider everything as fields. And now you have the field theory, right? And now you have the this tug of war between the particle theory and the field theory on electrical and thermal conduction and such, the dual role and such, right, that we saw last lecture. So this is something which was disturbing many people, right? And the other aspect, right, they were most eager to lose electrons. The idea of electrons came about somewhere around in 1800s and 1890s. J.J. Thomson decisively proved the existence of electrons and the charge and mass and such, right? So around 1900s, electrons were well known, and Dalton proved that the electrons had some relationship with the chemical bonding and such, and most metals were known to form very stable oxides, right? And oxygen is known to grab electrons, and hence metals should be known to donate electrons. So because they form stable oxides, they are most eager to lose electrons. So they had a lot of free electrons to spare, so to speak, right? So now we will go ahead and then see how classically a person called Paul Drude tried to explain that metals have good thermal and electrical conductors. Particularly, it is not just that they are metals. It is like if you have free electrons, then you are supposed to have good thermal and electrical conduction. This is what was the contention. Metals was just a tag that you add to materials which have free electrons. Okay, so now let's go ahead and then see the derivation of Droods law. But before we go in, we will once again look at a little bit of history, right, just to see what was known before Drude started to consider electrical transport. So we will just now talk about electrical transport. So the various idea of the existence of charge came about in about 1600. Right? They were discussing maybe in 1700s to 1600s to 1700s, even late 1500s, 1580 or right? So charge, static charge was discovered by rubbing silk on glass, amber on glass, amber on insulating materials, right? So they thought that charges are transferred. Charge was a fluid, and it is transferred from one material to the other when you rub, right? And Alexander Franklin was, I think you must have all heard about him. So he imagined charge to be a fluid which can be transferred from one insulator to the other. Insulator was something which could not conduct electricity, right? But at that time it was just, let's say they had this jar, right? And then if you rub on top of this jar, you were known to form some charges. It was not thought to be positive and negative yet. And if you put a metal wire on top, they saw that you can move this charge along the metal wire, but if you have an insulator, you cannot move it further. But if you rub on the metal wire, you are not known to generate charges, or not known to observe such generated charges. And this was the origin of the thought of an insulator and conduction. This was all happening from 1500s to 1700s, right? So this is a glass jar which was most commonly used by many others. So you stick a needle through a cork in this glass jar, and then you can extend the charges. The charges seems to flow. So they thought it should be some sort of a fluid. And in 1800s, particularly 1800, we had Alexandra Volta, who came and showed that you need not have to rub to generate charges. You can have a constant flow of charge if you have what is called as a potential. So he made a battery of sort by stacking different materials, and then he showed that you can have electric current or constant flow of charge from one place to the other. It always used to go from one direction depending upon the potential that was generated and such. Okay, and in 1838 we had Michael Faraday, who cleared the idea of charges. He said that the electric charges always appear in pairs. So you always had two polarities, and hence it was named positive and negative arbitrarily, right? One does not necessarily have to choose one kind of charge to be positive, but it was always thought to be occurred in pairs. That is, the charges occurred in pairs, and then the normal state is, this was a crucial thing, the normal state is an unpolarized state. So this already proved that you had some sort of a force between these two charges, the two polarities in which charges occur, and then they all want to get together to form a normal state in which nothing is polarized, right? So this was the origin of all these charges with which caused current flow and such. And in 1850s we had Maxwell, who cleared the thought of fluid regarding charges, and then said you have to consider all of them as fields. Then you have electric field and magnetic field, and then the famous relationship between the two. And when you will have current and you have a changing magnetic field, and then the relationship between the fields which will diverge, the magnetic fields do not diverge and such, right? So it is in this context that in 1900s we have Paul Drude, who came up with this transport property of electrons. To understand few aspects, the most important one being the relationship between the electric potential V and the current I. It was known that for most materials this is true, at least for some extent, that you had a linear relationship between the current and the voltage, and this linear slope is known to be the resistance, right? So this is the most famous law that we know, which was empirical till that point of 1900s, that you cannot know why this is true, but then the potential across the terminals determine what was the current, right? Given the same material, you increase the potential, obviously increase the current through them, and it was known to be a constant. So this was something to be explained in 1900s, and this is when Paul Drude came up with this classical theory of electron conduction, where he assumed that a metal, he thought of metal to be something like this, okay, some bar where you have atoms, right, in some order. He did not assume it to be in a lattice, some order, okay. All the atoms or some ion cores, does not have to be in lattice, and then you had electrons which move. And by 1890s, you know that Thomson came up with an idea of an electron, but remember, the idea of an atom was still the plum cake model, right? So basically you have a positive charge which is distributed, and then negative plums in a cake, and all these areas are positive charges in an atom. But Paul Drude still imagined the metal to be of this shape, because in 1910 only Rutherford came up with this famous experiment that we said previously, right? Shooting alpha particles and then saying that, oh, the positive charges cannot be distributed but should be concentrated. But nevertheless, in Paul Drude's case, he assumed you had ion cores, and then you had this electrons which are free to move. And he assumed this entire situation to be very similar to an ideal gas whose kinetics were well known at that time, right? So let us deviate a second and then go to this ideal gas and then understand what this ideal gas theory is before we proceed. Okay, so an ideal gas was imagined to be something like this. So you have a container. I'm just drawing it here so that we can compare these two. So let's say we have a container and you have a gas inside the container, and the gas is composed of a lot of atoms. Atoms was well known, right? Even at this time, the constituents of atoms were still in contention, right? But then atoms as such were well known. So the gas has a lot of atoms. So you have this random distribution of gases in a volume, and then you know that the gas in a volume will present some kind of a pressure, and the pressure is thought to be the force applied by these gas atoms impinging on the wall. So you have this gas atom, they impinge on the wall, and then they transfer some amount of kinetic energy to the wall, and it is this which causes the pressure in a particular known volume. The gas atoms were known to follow a few assumptions. So let us enumerate these assumptions. The first one being, you have a large number of small particles or atoms in a gas. Okay. The second one is the particles are identical, atoms are identical, right? In terms of composition, mass, they are all the same. You cannot distinguish one from the other, is what we mean by this. Their density is so large that you don't need to know the macroscopic details, that they can be treated statistically. So what we mean is, you can talk about an average velocity. So basically, if you have only a few atoms, let's say 3 or 4 atoms, right? So their velocities can be so largely different that you cannot actually mention a single velocity with a mean and a standard deviation, right? But if you have a large collection of particles, then you can establish an average velocity, and the deviation would not be significant in comparison to the average, right? So this is what they mean by thermodynamic properties, that you can have you can treat their properties statistically, where you can mention an average with the deviation being considerably smaller, right? 4, the particles collide among themselves and the wall, causing pressure. I'm going a little bit detail into this because this is something which we will need even in our further development of statistical thermodynamics. We will talk about various particles, electrons and phonons and such, why some particles show Fermi-Dirac distribution and why some particles show boson distributions. So some idea of thermodynamics is necessary for this course. So we build this kinetic theory of gases here because we are going to use the equipartition theorem. We'll very quickly prove the equipartition theorem, and that's where we are going right now. Okay, so the particles collide among themselves and the walls, and this is what gives you the pressure, right? The fifth point is, except collisions, the particles do not influence, right? The particles are independent except collisions. So the particles do not affect the way they move. So the particles are basically uncharged. They are like balls in a billiard board, right? They just move until they get collided. Otherwise, each one of them do not determine the way the others move. You can clearly see how this is not true in the case of an electron, but we don't go there yet, right? So this is what is the situation. Now let us look at the various aspects of this, and then let's see if we can draw some parallels between this picture and the metal picture, right? So this is pretty similar in some aspect. The electrons in a metal are also like to be confined in a volume, like a gas, as we shown here, right? And they move independent of each other. That is what the assumption of Drude was. We will continue further on what was the assumption, but then you can already see the relevance between the two, and this is why Paul Drude thought that the electrons in a metal behave very similar to atoms in an ideal gas. But if you have an ideal gas, and let's say in a volume, and this is a cube of side L, right? So now let's see a particle which is, let's consider this particle here, okay? It is impinging on the wall with a velocity, let's say along the x direction, to be Vx, right? So what will be the time in which, let me rephrase the question. What is the frequency of the particle impingement on one side of the wall? So let me write a particle. Here particles are allowed to move in all three directions, okay? A particle impacts a side of the wall in every time del t, which is given by twice the L by its velocity along the x direction here, okay? So this is something that I would like you guys to think about it and prove. This can be normally proved by just geometric considerations, right? And if you're not able to prove, you can always come back to me and I will give you a short proof of why this is to be true. So basically what we mean is, if Vx is the velocity and L is the side of the volume, the time separation between each impingement of a particle on one side of the wall will turn out to be 2L by Vx. Right? So the particle is known to scatter among itself and then move based on the velocity, on whatever velocity Vx. So here they have the thermal velocity, okay? So they just go and scatter among themselves as well as at the wall. This is the thought at this particular time, okay? Now at the wall, what is the change in momentum? So let's say a particle comes, hits at the wall, right? It gets scattered back at, let's say, minus px, and this comes in positive. So we are talking about one directional transport here, right? So a particle here, let's say, hits here, comes back. So if Vx is the velocity along the positive x direction, it gets scattered back in velocity minus Vx, right? So the change in momentum at the wall here, we are all talking about the same dimension, right? So think about it. I'm looking at a particle which moves purely along the x-axis, but this can also be true if the particle is not moving purely along the x-axis, right? Let's think about it for a second. Let's say I have a wall like this. I'm talking about something which moves perpendicular in Vx, gets scattered back in minus Vx, right? If this is not true, something is moving along this direction, right? So it has some component along Vx here and some component along Vy, right? So when it gets scattered back, we assume that the component along the x direction is again minus Vx, right? That's why the total change in momentum when it hits the wall will turn out to be p in that direction minus of minus p in the opposite direction, right? So which will turn out to be twice the momentum. So it will turn out 2m, m being the mass of the particle considered here, and Vx because we are considering only one direction, right? So what will be the total force on the wall? See, I'm trying to calculate the pressure, right? So because these are the global observables, so the force on the wall is change in momentum by the change in time, right? Because this is del t is how frequently an atom impinges, and del p is the change in momentum every time it impinges. So the relationship will turn out to be m Vx square by L. And obviously if there are n particles, the total force on the wall will turn out to be n times m. Now you have an average, right? Because you are n particles, you have average velocity, which is mentioned in this braces as we shown here. So L being the side of so this will be the average force, right? So now let's consider a particle which is moving in 3 dimensions, right? So something like this, let's say it has something. So it has some velocity along the x direction, which is vx. It has some velocity along the y direction, which is vy, and some velocity along the z direction, vz. And we know the Pythagoras theorem in 3 dimension, right? So which is the total velocity square is the velocity square in the x, velocity square in the y, and the velocity square in the z. And let's assume a particle in which all of these things to be the same. Then you know that the velocity square in 1 dimension would be the velocity square in the average velocity by 3, right? So because we are assuming it to be free, we assume it to be randomly going. So basically we are assume one direction in which it is equally it has equal values in all dimensions, right? This is just one assumption. Obviously this can change, right? That's why we talk about only average values. So if this is to be true, then the total force can be written as 1 by 3 n number of particles, m mass of each particle. Instead of vx, now we have the average velocity in 3 dimensions, right, by L. And the pressure is the force per unit area, so which will turn out to be 1 by 3 nm v square by L cube, right? L square is the average cross section, and L cube will turn out to be V, which is the volume. So pressure into volume will be 1 by 3 n m v square, correct? And from ideal gas law, you know the pressure into volume is n times kBT, K being the Boltzmann constant, T being the temperature, right? This is the ideal gas law or Boyle's law as we know it, right? And from here you can easily see kBT will turn out to be 1 by 3 m v square. And you know that the average kinetic energy of any particle, let's say the average kinetic energy of a particle, I am writing it as K, will be half m v square. Now I am taking v to be an averaged velocity. The particle, if you take one single particle, it will be just v square. But if you take multiple particles moving in random directions, you take an average of those velocities, the mass being the constant, the average kinetic energy will turn out to be the square of the proportional to the square of the average velocity, right? If this being true, you can say that this K will turn out to be 3 by 2 kBT, right? 3 being the number of dimensions, and this tells you that each dimension of freedom or each degree of freedom that a particle has adds 1 by 2 kBT energy to that degree of freedom, right? So this is what is called as the equipartition theorem. So the total energy is distributed equally among all the degrees of freedom, and this comes about because we assume that the velocity is equal among each dimension. So this came about from this assumption that we assume that the particle moves in constant velocities or approximately equal velocities in each dimension, right? So this gives you that the total velocity is about 3 times the velocity in any of this direction, and hence each of these dimension will add to 1 by 2 kBT times in each dimension, right? So this is almost the derivation for the equipartition theorem, which we will use in the Droods derivation. So now that we kind of understand the classical motivation towards motion of free particles. Now let's see. Now let's consider the Droods model. So now we go back to Droods model. The assumptions will follow the assumptions that the classical kinetic theory of gases take. So we are going to list the assumptions that the Drude used, and this is following Ashcroft and Mermin solid state physics book. So I would highly recommend you to look at this. This is among the most highly appreciated treatment of the Droods model, because they list a lot of aspects very clearly and lucidly, right? So in a metal, as we saw previously, we will go back to this picture of a metal, right? You have to have a number of these electrons which move freely. So how do you calculate the number of electrons? In a gas, it's simple, right? You just use the Avogadro number. But in a metal, you have to be a little bit more careful. So Drude assumed the number of electrons in a metal per unit cube, because we're looking at some standardized values. So if n is the number of conducting electrons, per centimeter cube, it was written to be an Avogadro number of 6.023. You can see the kinetic theory already, right? Avogadro number. Z being the valence of the metal, valence of the atom in consideration, which was already known from the chemical theory, right? Rho m being the mass density of the material by A, the atomic mass. So this gives you number of atoms that you will have into this per unit cube, right? And Z being the valence. So this is a very simple relation to give you the number of conducting electrons. It is thought that each atom in the volume, in the bulk of the volume per centimeter cube that we consider, will donate a certain number of electrons called the valence electrons for conduction. And this can be easily calculated by this if you know the valence Z, right? So with this, let's say the assumptions of Drude are listed like this. In the absence of any electromagnetic field, in the absence of EM fields, the electrons move in straight lines. Okay, and it is known, so basically the electrons have a constant mass, because Thomson had proved previously there what is the mass of the electron with the charge and such. It is known to have a particular mass, and Newton's classical laws hold. If you know the force on the electron, then you can calculate what is the acceleration, you can calculate what is the velocity at any time. All these things can be precisely known. Okay. The second aspect of this is any electron-electron interaction is ignored. So this is also called as an independent electron approximation. Electron. So basically all these things are a consequence of having electrons to move in straight lines. So in the sense that no further force is acting on it, right? So basically the electrons, there is no electron-electron interaction, and there is no electron-ion interaction other than collision. No. So what we mean is, this is also called as free electron approximation. What we mean is there are no long range Coulomb interactions and such, right? So basically the ions are not charged, the electrons are not charged, you don't have any attractive forces between them or repulsive forces between them. They just move as again balls in billiards depending upon the size. Electrons are of smaller pulses, the ions are bigger pulses. You scatter among a small one across the bigger one. They are elastic, they don't break apart, and then this just transfers the momentum, but it still does not transfer the momentum. Okay, so these are the small modifications from the classical thought that we will have between an electron and ion collision and the ball and ball collision. In a ball and a ball collision, you can clearly see that the momentum gets transferred, right? So basically, if it hits, goes back in a velocity can be calculated from its previous velocity. Now we go to the deviation from the classical ball-ball interaction model, right? So the electrons are known to collide of ions. Electrons collide of ions, which is what we saw previously. But then this is a slight deviation from the kinetic gas model, because in the kinetic gas model, electrons collide with each other. I mean, the atoms collide with each other as well as with the walls. So here the electrons are not thought to collide with each other, but they collide with different static particles called as ions. Okay, so the electrons collide of ions and the collision is instantaneous. So what we mean is that the electron, let's say, goes with some velocity Vx and then hits an ion. It gets scattered in a random direction. You do not know what direction it can get scattered to. But when it gets scattered to, so basically this picture itself is not exactly correct, because it is continually accelerating from the previous collision. Okay, the velocity is continually increasing since the previous collision, and when it hits, it starts at not depending upon the velocity at this point, but then at VTH at this point, right? And then starts accelerating in a different direction. The same thing can happen in the other direction. So this is what is called as the collision, which is instantaneous. After the collision, it starts with the velocity which is determined by the thermal velocity and not by its previous velocity. These are the assumptions, right? If you assume that it starts from the previous velocities, then things can have different consequences. We don't go off there. Okay, so this is an aspect which is different from the classical ball-ball model. The third part is the probability of the collision. In a unit time is assumed to be 1 by tau. Tau is known to be the relaxation time. This is just a model parameter, right? So every model has some parameters. This is something that you can measure experimentally, but this is something which is used almost universally. And even though Droods model had several shortcomings, this is something which is used even till now. So basically you have what is called as a relaxation time, or the probability of collision in a unit time, which is 1 by tau, and there are certain consequences of this definition. So what it tells is that an electron picked at random faces a collision. The consequence of this definition, this is something again that you will prove in your homework, is that the consequence of this definition is that the electron picked at random faces a collision after a mean time tau seconds. Okay, so this is what is the consequence of this, or you can say that the average lifetime is tau, the mean lifetime, average lifetime is tau. The fourth is it is probably not an independent assumption, but it's a follow through from all the previous assumptions, and this is something that I said slightly before. The electrons achieve thermal equilibrium only via collisions. because they should finally come up with an average velocity for all of them, right? Because the electrons and electrons do not collide with each other. We still assume a constant average velocity at steady state. As you will proceed through in our derivation, we will see that we'll assume that there exists an average thermodynamic velocity, and that average velocity is obtained just purely by collision, and after each collision the velocity turns back to the thermal average and then starts. So the thought is, okay, let me explain this again. So basically, if we have an atom like this, another ion like this, another ion like this, you have an electron like this, electron like this, and electron like this. Each one of them is traveling at very different velocities, right? But then there is an overall constant velocity, average velocity. How do we get this average velocity? It's that it moves, it accelerates to some ion, okay, scatters away from this ion, but as it scatters, it again begins with VTH, that is the thermal velocity, and again starts to average. And because of the fact that there exists a relaxation time tau, that is an electron picked at random faces a collision after tau, which is constant for all the electrons, their velocity can be assumed to have an averaged value, which is true for, let's say, because for the countless number of electrons that we have assumed in a metal, right? I think I have made the point here. So the electron, because you have an averaged scattering time, and after each scatter it starts not from its previous velocity but from the thermal velocity, you can assume that the collection of electrons will arrive at an averaged velocity after a significant time. Okay, so these are all the assumptions from Drude. So now let's proceed to derive the electron conduction from the Droods model, from all the assumptions that we made before. So we will take a little bit different approach from what we did in the previous course. So people who have already taken 614, who might have already seen this a little bit, can also learn something new from here. So let's consider one electron at a time, and let P of t be the momentum of the electron at any time t. So basically I take this bar, right? A lot of electrons are there. They are moving in random directions, and they can scatter off these big ions at any time t. So this is some time snapshot at time t, right? It's moving, and for any small time duration dt, the probability that the electron will suffer a collision, let's say at time t plus dt being small, the probability of the electron to suffer a collision is basically dt by tau, right? Because the average time for an electron to collide is tau, and if time is dt, which is some unknown value, the probability for it to have a collision is dt by tau. This is normal probability theory, right? So if this is true, then the probability that the electron did not collide in time dt is 1 minus dt by tau, right? This again should be true because total probability should be 1. So this is true, right? And if we assume some external force, now I'm assuming a general scenario. Okay, we are not assuming just DC potential. We are going to develop a general model which can be used in several applications, right? So let's assume an external force. It can be anything. It can be electric field, it can be magnetic field, it can be anything. Let's assume an external force which is also time dependent. I'm writing it as F of t. This is an external applied force. Okay, then the total momentum at time t plus dt, right, will be, it should be sum of both. So basically at time t it was p of t as we saw previously. At time dt, right, we know that it is accelerating because of this particular force, and the probability that it does not collide in time dt is 1 minus dt by tau. This we saw, and it is accelerating, so the velocity and the momentum should add, right? So I have the previous momentum plus the acceleration, the force that is provided on the electron, times the time. So this is the addition due to acceleration. You can also have a second order function which is function of dt square, which I'm going to ignore for now, right? So this is the first order effect of acceleration. This is the second order effects which we are going to ignore for now, right? So this is true. Now you should ideally also have the effect of things which got scattered, right? So now you see that if this is true, if it got scattered, the addition that can have should have, let's say, a function of the force again by time. So basically you will always land up in something which is order of dt square if you consider the electrons which got scattered. So typically we ignore this because any term which includes something which got scattered has dt by tau, which we will ignore, right? So now if I expand this, you get p of t, which is the original one, minus p of t dt by tau, right, plus f of t dt minus something order of dt cube, which is again much smaller, right? So I'm going to ignore this. So this is the total term, and you can obviously bring this to the other side and divide everything by dt. So now you will get dp of t by dt, which is a differential form of this expression, which will turn out to be minus p of t by tau plus f of t. F of t is the forcing function, and this expression, which is called as the equation of motion for an electron, which is assumed to be in the classical kinetic theory of gases regime, was developed by Drude. So this is the electron equation of motion. So we have neglected all the second order terms. We have neglected the fact that electrons which got scattered will affect the subsequent momentum, and considering only the aspect of electrons which is moving forward in time dt, we have calculated this, and here it is easy to see that the momentum change or the scattering which causes the momentum change just acts as a damping effect on the momentum, total momentum, right? So this is the damping term. If anybody who has seen the first order differential equation and their solutions, you can clearly see that you have an exponential decay of electrons which got scattered by time, right, which is traveling in a direction. Let us say that you have n number of electrons, which is moving in a particular direction or which is going unscattered. It is this one, it says that it goes down exponentially and drops to n by e at time tau, right? So basically the number of electrons which go unscattered decay exponentially. This is sort of a damping behavior which is seen in most first order differential equation examples, right? So this is called this is pretty normal, and this is pretty intuitive. This is how we think things happen, right, in many cases. Now that we know the equation of motion, now we can calculate various aspects. The first thing that we will calculate is DC conductivity. DC conductivity, we know the forcing term is some applied electric field E. We know that the force on each electron is E times the applied electric field, right? E being the force on the force on the electron, the charge is minus E, and E being the applied electric field, right? If this is true, and we are talking about DC, so when things are at steady state, you don't expect any change in the average momentum of electron. So now we move from single particle picture, as we saw here, to an average space. So we will going to write the average change in the electron momentum is going to be 0, because we have assumed DC operation and steady state, right? So we assume that the electrons are all moving in particular velocity, averaged velocity, due to the applied electric field E, and the averaged momentum is constant, right? Under this scenario, you can clearly again substitute this in here, and then you can see minus P average. So actually you don't do this. This itself is average by tau minus EE turns out to be 0, and this can be written as M average V. Let's say in one direction we talk about X. Again, this is true in the same way that we talked about the previous kinetic gases model, okay? Minus E tau, and the average along the X direction will be minus E tau by M to E. Now we know the average of velocity, right? So let me not go into the direction for now. Let's have something like this, and the current density J, let's take a bar here, right, in 2 dimension, right, and a cross section A, right? The current is, let's say, number of electrons which crosses this bar in per unit time, and if we assume an average velocity V, the current density can be written as number of electrons which cross this with a known velocity V, right? We can, okay, so we can actually derive this, because this will turn out to be this will turn out to be the current, because the current is basically number of charges which move. The number of charges is NE, and we know that the average distance that they move, let's say, is L in unit time dt, and L by dt will turn out to be the velocity, right? So this will be the average velocity, and this will be the average current, and we have calculated the velocity here. The current will turn out to be minus N E square tau by M into E, and from here you can see N is a constant depending upon the material, E is a constant, tau is assumed to be a constant, relaxation constant, and M is the mass of the electron, which is again a constant. So this entire thing was known as sigma, or the conductivity, which is purely a material parameter, which will turn out to be minus N E square tau by M, right? And this is a different form of our Ohm's law. V is an this is again just the Ohm's law, right? So we have derived or came up with an expression for a Ohm's law, and we have calculated what is the proportionality constant, or the resistivity or the conductivity of this material, and what it should depend on. It depends upon the number of electrons that it has, the mass of these electrons, and the relaxation constant tau, right? Now, though this seems to be good and works well, we will see soon that there are several examples in which this can be wrong, and the value of this relaxation constant, which is a parameter which was introduced in this model, can be extracted back from experiments, and it was found that this value turns out to be somewhere around few angstroms, right? Some 10 to 100 angstroms. So which means that the electrons scatter with so this is among the atomic distances. Okay, so Drude thought that the electrons scatter at ion cores or atoms cores, and this was shown to be experimentally false because in reality electrons were shown to move distances of the order of microns to centimeters. So this was something which troubled experimental researchers for some time, and this makes us to go and explore other models which will slightly change the Drude's approach, but we will get back to that later on. Okay, so this is the first consequence of kinetic theory of electrons. The second one can also be easily proved is the Hall conductivity. Hall's experiments were something like this. It requires a three-dimensional view. So let's take an electron, a metal bar. You apply some current I, right, and at some known potentials V, and if you apply a magnetic field which is perpendicular to this, a transverse potential was observed, right, and this transverse potential was known to be proportional to the applied magnetic field B. Well, there was no transverse current, so you have Ix, but Iy was known to be 0. You don't have any transverse current. The current is only along the x direction, and because of the applied magnetic field B, you always had the a transverse potential Ey. Now to explain this observation, let's once again use our previous equation of motion, which is dp by dt is equal to average p by tau plus f of t. And here f of t is again a forcing function, and we are again going to assume this is DC Hall. We are not still going to AC, right? And the forcing term is now Lorentz based, right? Because now you have an electric field and a transverse magnetic field. Under these situations, you know the forcing term will turn out to be EE minus EV cross B. V being the velocity, right? And the velocity has different dimensions. And let's assume that we are talking about an averaged velocity along the x direction, right? So this is along the x. So you have an average velocity Vx along the x direction, and we have an average velocity Vy along the along the y direction, right? So let's once again, this will turn out to be 0, right, because we're talking steady state. So the momentum along the x, momentum change of the averaged value along x and y is going to be 0. So this will turn out to be 0, and we have an averaged x momentum by tau minus Ex. This is the average velocity, field along the x which is applied, right? And now if you assume, see, this V is now Vx, Vy, Vz, right? And B is Bx, By, Bz. And we assume the magnetic field is normal, so Bx and By are 0, and you have only Bz which is present. So when you have only Bz which is present, you know the terms, right? So if you do a vector multiplication, it will turn out to be minus omega c py, and here I have put omega c to be EB by m. Okay, omega c is known as the cyclotron frequency. We will look at it later on, but it's just a simplification. I just did vector multiplication and substitution. The same way you will get another one. We have py by tau minus Ey plus WC Px. Because this is vectorial, right? So I'm going to distribute these two components and then I write it in this particular fashion. The electric field is again a vectorial field. You have an electric field Ex and Ey. The velocity and all of these things are vectorial. Right? But then each vector also has its averaged value. We are all talking about averaged values. Now if I multiply each one of this by Ne square tau by m, I will get this. Sorry, Ne tau by m. Okay, I will get Ne square tau by m Ex will be equal to Jx, because Ne square tau by m, Ne by m into Px will be the current, right? Nev is the current. So Ne by m into P, m and m will cancel, you will get the current plus omega c tau Jy. Ne again multiplied by P will give you the current. The same thing, and this is sigma, right? So I'm going to write sigma Ex is Jx plus omega c tau Jy, and doing the same thing to the second equation will give me Jy plus minus omega c tau Jx. Remember, experimentally we know that Jy is 0, right? So if I put this to 0, the second equation will simply reduce to Ey will be minus omega c tau by sigma Jx, and this Ey is the transverse potential as we saw previously, right? And this relationship is basically the Hall effect, and this can be reduced to minus b by Ne into Jx, and RH, which is called as the Hall's resistance, will be minus 1 by Ne. It is called as Hall's resistance, right? So this very simple derivation shows that you can use the Droods approach or the classical approach to explain why do you have a transverse potential when you apply a magnetic field perpendicular to the metal, and you have something which is called as the Hall's resistance, which is the resistance divided by the applied magnetic field, which is constant and depends only on the number of electrons that you have. So basically it shows that the Hall resistance is negative for all metals because you only have to change the number of electrons that it has. The Hall's resistance is independent of the potential that you have applied. It is linear and it just depends upon the number of electrons that the material has, and which was known to be not true for several materials, particularly like aluminum and such, where it shows positive Hall coefficients, positive Hall resistances, right? But we will see the downside of the Droods model in the next class. But these are the consequences of very simple assumptions that you begin with, assuming that the electrons in a metal behave like gases, like an ideal gas in a volume. So you can clearly prove the DC conductivity, you can prove the Hall effect, And you can also come up with an expression for AC conductivity, which we will not deal with now, but later on when we talk about optical interactions of electrons and materials, we will touch upon the electrical conductivity that can be extracted from the Droods model. So with this, I stop this lecture, and I encourage you to post any comments and questions that you have. Thank you.